Nobody made a big announcement. That's the part that stays with me. In July 2024, inside a crater on Mars that used to be a lake billions of years ago, a rover drilled into a rock and pulled out something that, if it were found on Earth, wouldn't even be debated. It would be called what it is, a sign of past life. Instead, the response was careful, slower than you'd expect, almost hesitant. And if you read the actual paper, the one released by NASA and the Jet Propulsion Laboratory, you notice something strange. The language bends around the conclusion. Words like suggestive, consistent with, non-biological explanations cannot be ruled out. Technically correct, scientifically responsible, but also incomplete. Because what the rover found inside that rock, named Chayava Falls, wasn't just one thing. It was a combination: organic molecules, carbon-based structures, mineral formations that, on Earth, are usually built by microbes. Not always, but often enough that geologists don't ignore it. And that's where this stops being a story about Mars. Because the real question isn't, did life exist there? It's, how much evidence do we need before we allow ourselves to say yes? If this sounds like scientists being cautious, that's because they are. They have to be. NASA has spent decades building credibility around not jumping to conclusions, especially after earlier Mars missions in the 1990s made claims that didn't fully hold up. But something changed with Perseverance. Not just the rover itself, the instruments it carries. Sherlock, for example, a spectrometer designed to detect organic compounds at a microscopic level. It doesn't just say, there's carbon here. It maps how that carbon is structured, where it sits in the rock, whether it's random or patterned. And patterns are where things get uncomfortable, because random chemistry doesn't usually organize itself in ways that look intentional. Not at that scale, not repeatedly. In the Chayava Falls sample, researchers identified vein-like structures filled with calcium sulfate, basically mineral deposits left behind by flowing water. Inside those veins, organic material, not scattered, embedded, which suggests timing. Water flowed, minerals formed, organic compounds were present at the same time, possibly interacting. On Earth, that's not ambiguous. That's biology until proven otherwise. On Mars, it becomes a debate. Here's the part most coverage skips. Mars wasn't always the place we imagine now. Cold, dry, almost static. 3 to 4 billion years ago, it had rivers, lakes, a thicker atmosphere, magnetic protection from solar radiation. In other words, the same basic conditions under which life appeared on Earth. Not guaranteed, but possible. And Jezero Crater, the place Perseverance landed, wasn't chosen randomly. It was selected because orbital data showed a delta, sediment deposits where water once flowed into a standing lake. The kind of environment where, on Earth, microbial life tends to thrive, and more importantly, where it tends to get preserved. So when Perseverance drills into a rock in that exact location and finds organic material embedded in mineral structures formed by water, you don't just dismiss that. You pause. There's a number NASA hasn't emphasized publicly. Not because it's hidden, but because it's easy to overlook unless you're reading the technical details. The organic compounds detected weren't simple. They weren't just methane traces or basic carbon signatures that could come from geological processes. Some of them were more complex, aromatic structures, rings of carbon atoms that are harder to form randomly. Still possible without life, but the probability narrows. And this is where the language becomes careful. Because science doesn't deal in probably when the claim is this large. It deals in proof, repeatability, elimination of alternatives. Could these compounds have formed through abiotic chemistry? Yes, under certain conditions. High harara, specific mineral interactions, long timescales. But those same conditions also overlap with environments where life thrives. So you get this overlap, this uncomfortable middle space where both explanations are technically valid. And no one wants to be the person who declares life and turns out to be wrong. There's a moment, reading through the data, where the scale of it shifts. Because this isn't about a single rock anymore. Perseverance has collected multiple samples, different locations, different geological contexts. And while not all of them show the same level of organic complexity, enough of them do to suggest this isn't an isolated anomaly. It's a pattern, a faint one, but consistent. And here's where it gets quiet. Those samples aren't being fully analyzed yet. They can't be. The instruments on Perseverance are advanced, but they're still limited compared to what we have on Earth. The real analysis, the kind that could actually confirm biological origin, requires labs we haven't sent to Mars. So NASA made a decision years ago. Collect the samples, seal them, and bring them back. The Mars Sample Return Mission. Planned, funded, delayed. As of now, the earliest realistic timeline for those samples to reach Earth is sometime in the 2030s, which means we may already have the closest thing to evidence of life beyond Earth, sitting in sealed titanium tubes on another planet, untouched. And this is where I keep coming back to that silence, not as a conspiracy, not as suppression, but as a kind of restraint. Because if you say it too early, and you're wrong, you lose credibility for decades. If you wait until you're certain, you might be sitting on one of the most important discoveries in human history, saying nothing definitive for 10 years. That's the trade-off, and I'm not sure we've fully processed what that means. There's something else, though, a detail that doesn't fit neatly. It has to do with how these organic structures are distributed within the rock, and why some scientists are more intrigued than others. We'll come back to that. What makes this harder isn't the presence of organic material, it's the pattern it forms. Because if you zoom in, really zoom in, to the microscopic mapping done by Sherlock, you don't just see carbon sitting there like dust. You see clustering, specific regions inside the mineral veins where organic compounds are concentrated, while adjacent areas remain relatively clean. That distribution matters. On Earth, when microbes live inside rock, endolithic life, buried within mineral structures, they don't spread evenly. They colonize microenvironments, tiny pockets where water, nutrients, and protection align just enough to sustain them. The result isn't uniform chemistry. It's patchy, selective, almost intentional looking, even when no intention exists. The Shyava Falls sample shows something uncomfortably close to that. Not identical, not definitive, but close enough that geologists studying terrestrial analogs paused when they saw the data. And that pause tells you more than any headline. There's a tendency to think of life as something obvious once it appears. Plants, animals, visible movement. But for most of Earth's history, life was microscopic. For nearly 3 billion years, it didn't build forests or ecosystems we'd recognize. It lived in films, in sediments, inside rocks. Which means if Mars ever hosted life, this is exactly what we'd expect to find. Not bones, not fossils in the traditional sense, chemical fingerprints embedded in ancient geology. And that's what makes interpretations so difficult, because chemistry can imitate life under the right conditions. Given enough time, energy, and the right catalysts, non-biological processes can produce molecules that look familiar. The argument from the cautious side is straightforward. Mars is chemically active. Volcanism, water-rock interactions, radiation from the sun. These can create organic compounds without biology. We've seen versions of this in laboratory settings, and they're right. But the counterpoint isn't weaker, it's just less comfortable. Because when you layer multiple indicators together, organic molecules, water-deposited minerals, specific structural patterns, the probability that all of them emerged independently, without any biological process involved, starts to stretch. Not impossible, just increasingly specific. There's a paper published in Science Advances that doesn't get mentioned much outside academic circles. It focuses on biosignature detection thresholds, basically how much evidence is required before scientists agree something is biological. What's interesting is not the threshold itself, but how it changes depending on context. On Earth, the threshold is lower. We know life exists here, so ambiguous signals are often interpreted through that lens. On Mars, the threshold is higher, much higher, because the cost of being wrong is enormous. So the same dataset can be interpreted differently depending on where it's found. That's not bias in the usual sense. It's caution scaled to consequence. Still, it creates a strange asymmetry. If Shyava Falls were a rock from Earth's ancient seabed studied in a lab in California, there's a real chance it would already be labeled as evidence of past microbial activity. On Mars, it becomes a question mark. And then there's the mission architecture itself. Perseverance isn't designed to answer the question completely. It's designed to ask it better. That sounds abstract, but it's very intentional. The rover's job is to identify promising samples, document their geological context, and store them in sealed tubes. Ultra-clean, isolated from contamination. Each tube is effectively a time capsule, preserving not just the material but its relationship to the surrounding environment. Because context is everything. An organic molecule on its own is interesting. The same molecule embedded in a sediment layer formed in a standing body of water alongside specific minerals, arranged in a particular structure. That's evidence. Not proof, but evidence that accumulates. So Perseverance collects, labels, moves on. 43 sample tubes in total, if the mission completes its plan. Each one a piece of a larger puzzle that no single instrument on Mars can fully solve. Which brings us back to the delay. The Mars sample return program was supposed to be straightforward, at least on paper. A follow-up mission lands near Perseverance, collects the cached tubes, launches them into Mars orbit. Another spacecraft captures them and brings them back to Earth. Simple sequence, extremely difficult execution. As of 2025, cost estimates have ballooned past $11 billion. Timelines have slipped. NASA has started reevaluating mission architecture, considering smaller, more distributed approaches to reduce complexity. Translation: it's no longer clear when, or even exactly how, those samples will come back. And until they do, the most decisive analysis remains out of reach. Because Earth-based labs can do things no rover can. Isotope analysis at extreme precision, electron microscopy at resolutions far beyond what's possible remotely, techniques that can distinguish between biological and non-biological origins with much higher confidence. Right now, we're looking through a window. The glass is clean, but it's still there. There's a quiet irony in all of this. Humanity has spent decades asking whether we're alone in the universe. We built telescopes, launched probes, mapped distant exoplanets. We imagined the answer would come from somewhere far away, another star system, a distant signal. Instead, the most compelling evidence might be sitting 225 million kilometers away, locked inside rocks we've already collected, not screaming for attention, just waiting. I keep thinking about a researcher quoted in one of the mission briefings. Not a headline figure, someone working directly on the data. They didn't say, "We found life." They said, "This is the kind of sample we came here hoping to find." It's a careful sentence, but if you read between the words, it carries weight. Because it implies expectation, preparation, a recognition that this, whatever this is, fits the pattern they were looking for. And yet, the conclusion remains deferred. There's another layer here, though, one that complicates the entire picture. It has to do with contamination. Not from Earth to Mars, but the other way around. And why bringing these samples back isn't just a technical challenge. It's a philosophical one. There's a version of this story where the only risk is being wrong. That version is incomplete. Because the moment you seriously consider that these samples might contain biological signatures, real ones, not just chemical echoes, you also have to confront a different question. What happens when we bring them here? Not metaphorically, physically. Back to Earth. NASA doesn't talk about this casually, but the framework exists. It's called planetary protection, and it's been part of space exploration policy since the 1967 Outer Space Treaty. The idea is simple on paper. Don't contaminate other worlds with Earth life, and don't bring back something that could disrupt Earth's biosphere. Simple principle, extremely complex execution. For Mars sample return, this translates into containment protocols that go beyond anything used in previous missions. The samples would be sealed on Mars, transferred in orbit, recontained during re-entry, and then handled inside a facility more restrictive than a BSL-4 lab, the kind used for Ebola and other high-risk pathogens. Because we don't know what we're dealing with. That uncertainty isn't paranoia, it's procedure. Now, to be clear, most scientists don't expect Martian life, if it existed, to be dangerous in any conventional sense. The biochemical compatibility alone is a massive question. Life that evolved independently might not interact with Earth biology at all. Or it might. We don't have a second example of life to compare against. Every organism we've ever studied shares a common ancestry. DNA, RNA, the same basic molecular machinery. Even viruses, as strange as they are, operate within that framework. Mars, if it hosted life, could represent something entirely different. Not hostile, just unfamiliar. and unfamiliar systems don't always behave in predictable ways. This is where the conversation quietly shifts from science to philosophy, because the hesitation around declaring life on Mars isn't just about data quality, it's about consequence. The moment that statement becomes official, it changes something fundamental, not in a dramatic, cinematic sense, but in how we understand biology, evolution, even our place in the universe. If life emerged twice, independently, within the same solar system, then the universe is probably full of it. Not rare, not exceptional, just common. And that reframes everything from how we search for extraterrestrial intelligence to how we think about Earth itself. It also raises uncomfortable follow-up questions. If life is common, why don't we see more of it? Why no clear signals, no obvious biospheres on nearby worlds? Why silence at larger scales? That's not a new question, but it hits differently when the first data point might be sitting in a metal tube on another planet. There's also a more immediate, less abstract consequence. Funding. NASA operates in a political environment. Budgets are negotiated. Priorities shift with administrations. A confirmed detection of past life on Mars would redirect attention and money almost instantly. Mars sample return would no longer be just another mission. It would become the mission. Timelines would compress. Risk tolerance might change. And that creates its own pressure. Because science moves carefully. Politics doesn't. So there's an incentive, unspoken but real, to be absolutely certain before making a claim that large. Not just scientifically certain, but institutionally ready. Otherwise, you risk triggering a cascade you can't fully control. Here's the reversal that complicates everything. The silence we're interpreting as caution might also be a form of honesty. Not withholding, not avoidance, just an acknowledgement that we're at the edge of what current instruments can resolve. Because when you look closely at the Sciava Falls data and the other samples with similar signatures, you see something consistent, but not decisive. A pattern that suggests biology, without excluding chemistry. And that's a hard place to sit. It's easier, in a way, to have no signal at all. Clean absence. No ambiguity. You move on. This is different. This is standing in a doorway without knowing which room you're entering. There's a technical detail that rarely makes it into public discussions, but it matters. Isotopic fractionation. On Earth, living organisms tend to prefer lighter isotopes of elements, like carbon-12 over carbon-13, because they're easier to process chemically. Over time, this creates measurable imbalances in biological material compared to non-biological sources. It's one of the strongest indicators of life we have. Perseverance can't measure isotopic ratios with the precision needed to make that call. That requires lab-grade instruments, the kind sitting in facilities on Earth, waiting for samples that haven't arrived yet. So even if the Sciava Falls rock contains that signature, if it carries the isotopic fingerprint of past life, we wouldn't know it yet. We're looking at a shadow of the answer, not the answer itself. And still, the pattern holds. Multiple samples, multiple detections of organic material, geological contexts that make sense for habitability, structures that resemble but don't confirm biological origin. Each piece on its own is insufficient. Together, they form something harder to dismiss. Not proof, but pressure. I keep coming back to that original observation. Nobody made a big announcement. Maybe that's exactly what you'd expect at this stage. Careful language, incremental updates, peer-reviewed papers instead of press conferences. Or maybe it reflects something deeper, that we're closer than we're comfortable admitting, and not quite ready for what that implies. I'm not entirely sure. What I am sure of is this. If those samples come back in the 2030s, and the data tips even slightly toward a biological origin, the shift won't be loud at first. It'll be quiet. A paper. Then another. Careful wording. Gradual consensus. And then, almost without a single defining moment, the answer to one of humanity's oldest questions will have changed. So here's the question I can't shake. If we already have 70% of the evidence, and the remaining 30% is sitting in sealed tubes on Mars, are we waiting because we need better data? Or because we're not ready to live with the answer? I think we'll know within 15 years. Not because the science will suddenly become easier, but because the pressure, scientific, political, philosophical, won't allow indefinite ambiguity. My bet? The conclusion won't be a clean yes. It'll be something more unsettling. Everything we see is consistent with past microbial life, and no non-biological explanation fully accounts for the data. That's not a headline people celebrate. It's one they sit with for a long time. If you're still here, you already understand this isn't just about Mars. It's about how close you can get to an answer before the question itself starts to change. And that's the part people underestimate. They think the discovery, if it comes, will feel like a switch flipping. One day we're alone, the next day we're not. Clean, binary, easy to explain. It won't feel like that. It'll feel like this. A slow accumulation of evidence that becomes harder to argue against than to accept. Papers stacking on top of papers. Language getting slightly less cautious each year. Suggestive turning into compelling. Compelling quietly becoming best explained by. No single moment you can point to. Just a line we cross without noticing. There's a historical pattern here. When oxygen first began accumulating in Earth's atmosphere around 2.4 billion years ago, the Great Oxidation Event, it didn't announce itself. It built gradually, molecule by molecule, until the chemistry of the planet had changed completely. No organism at the time would have understood what was happening. From their perspective, the world just shifted. We're standing at something similar, not chemically but intellectually. The difference is we can see it coming. Let's return to that number I mentioned earlier. The idea that some of these organic structures are complex enough to narrow the range of non-biological explanations. What does narrow actually mean here? It means scientists can list the possible chemical pathways that might produce those compounds without life, and then start eliminating them one by one. Too much heat? The surrounding minerals don't show evidence of it. Too much radiation? The structures would degrade differently. Wrong environmental conditions? The sediment layers suggest stable water presence, not extreme volatility. Each constraint removes a pathway, and when enough pathways are gone, what remains isn't certainty. It's isolation. The biological explanation doesn't get proven directly. It becomes the last one still standing. That's how this usually works. There's also a timing problem that doesn't get enough attention. Mars lost most of its atmosphere around 3 to 3.5 billion years ago. After that, surface conditions became increasingly hostile. Radiation, temperature swings, loss of stable liquid water. If life existed, it likely didn't last on the surface, which means any biosignatures we're finding now are ancient. Frozen records from a window of time that closed billions of years ago. That matters because it limits what we can expect to find. We're not looking for living systems. We're looking for traces left behind by systems that had just enough time to exist, and then disappeared. That's a very specific kind of evidence. Subtle, degraded, easy to misinterpret, and yet somehow, still there. There's a quiet argument some researchers make, not in press releases but in discussions, in conference Q&As, in the margins of papers. It goes like this. If you design a mission specifically to find biosignatures, and you land in the most promising environment we can identify, and your instruments detect multiple lines of evidence that align with biological processes, at what point does continued caution become a kind of denial? Not intentional, not political, just a reluctance to cross a conceptual threshold. Because once you cross it, you don't get to go back. I don't think NASA is hiding anything. That's the wrong frame. If anything, they're doing what institutions do when the implications of a finding extend beyond the data itself. They slow down. They let the evidence harden. They wait for independent confirmation, for multiple teams to reach the same conclusion from different angles. It's frustrating if you want answers quickly, but it's also the reason scientific claims, when they finally land, tend to hold. Still, there's a cost to that approach. Time. And in this case, time isn't neutral. Because while we wait for samples to return, for instruments to confirm, for consensus to form, the interpretation of what we already have continues to evolve, quietly. Here's my read on it. Opinion, not certainty. We are no longer asking, is there any evidence of life on Mars? We're asking, is the remaining uncertainty small enough to accept a biological explanation? That's a different question. And it's much harder to answer because it forces you to weigh probabilities, not just detect signals. The doubt I keep circling back to is this. What if the ambiguity never fully resolves? What if, even after Mars sample return, after isotope analysis, high-resolution imaging, every test we can run, we still end up with a conclusion that sits just short of absolute proof? Not because the evidence is weak, but because ancient biosignatures are inherently incomplete. Would we accept that? Or would we keep searching for a cleaner answer that might not exist? Because the universe doesn't owe us clarity. It gives us data. We decide what it means. My prediction is less dramatic than people expect and maybe more disruptive. Within the next 10 to 15 years, assuming the samples make it back and the analysis proceeds as planned, the scientific consensus will shift to something like this. Mars very likely hosted microbial life in its early history. Not confirmed in the sense of a living organism under a microscope, but supported by multiple independent lines of evidence that collectively outweigh non-biological explanations. That's where this is heading. Not a headline that ends the conversation, a conclusion that starts a new one. And when that happens, the question changes again. It stops being about Mars. It becomes about everywhere else. If life emerged twice, here and there, under broadly similar conditions, then Earth isn't a miracle. It's a pattern. Which means every ocean world, Europa, Enceladus, even exoplanets we're just beginning to study, moves from maybe to probably worth checking very seriously. That's not a philosophical shift. That's a strategic one. It affects where we send missions, how we design instruments, what we prioritize in the search for life beyond Earth. There's a strange calm to all of this. No announcement, no moment of collective realization, just a gradual adjustment to a new baseline. We might not be alone, and we've been holding the first real clue in a sealed tube on a cold planet for years. If you've made it this far, you're already thinking about this the right way. Not as a single discovery, but as a process unfolding over time. I'll keep tracking it as the data comes in.